All right. Hi, everyone. We're back at it with lecture 14. Exam 2 isn't for a while, so ignore that. Exam 2 is, in fact, after the break, so when we get closer, I'll start putting it on the pages. So now we're going to be talking about zeros of polynomials, rational functions. Okay. In previous lecture, we looked at complex numbers and stuff, and we'll be using that again today. So, real numbers versus complex numbers. Consider this function. F of x is equal to x to the fourth minus x cubed minus 3x squared minus 9x minus 108, right? Well, we want to see what this factors into. For real numbers, it factors into x minus 4 times x plus 3 times x squared plus 9, right? This factorization has 3 factors that are linear or quadratic, right? These first two are linear, the second one is quadratic. So it has how many real zeros? It only has 2 real zeros. Reason being, the 2 linear factors obviously give you real zeros, and the second one, if you try and set that equal to 0, you will get plus or minus the square root of negative, or plus or minus the square root of -3, which is not a real number. So if we look at complex numbers, this function f of x factors into x minus 4 times x plus 3 times, well, as I just said, if we solve for x squared plus 9 equals 0, we have x squared is equal to -9, x is equal to plus or minus square root of -3, x is equal to plus or minus 3i. Okay, so this would be x minus 3i times x plus 3i. And so this factorization gives 4 factors that are all linear. Okay, and it has 4 complex zeros. Okay, real numbers, when you try and factor a polynomial down, you won't always get linear factorizations. For complex numbers, you will always get linear factors. It's the way complex numbers work, which is quite nice. So let's move on to something a little bit more general. Suppose that f of x is a polynomial with real coefficients and degree n. So for the case of real numbers, f of x has at most n zeros, right? But it doesn't have to be n zeros. For complex numbers, f of x has exactly n zeros, which includes duplicates. So for instance, if you had something like f of x is equal to x minus 1 squared, right? That would be a 0 that is duplicated, right? So also for real numbers, f of x factors into linear or unfactorable quadratic factors. Complex numbers, your function f of x factors into n linear factors, again, including duplicates. And it has this form, f of x is equal to some constant a times x minus c1 times x minus c2, and so on, where each of these ci is a complex number, right? And just to be clear, you probably remember this from last time, but a complex number is a plus bi, where a and b are real numbers. So b can be 0, right? The reals are a part of the complex numbers. So you could have this be x minus 3, x minus 2i, x plus 2i, and dot, 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 right? Okay. Complex solutions occur in conjugate pairs. So like I've written here, you can't just have x minus 2i be a solution and not have x plus 2i not be a solution, right? If you get one, you have to have the other. So that's another good thing about complex numbers is once you have one of the complex solutions, you get its conjugate for free. Okay. All this factoring, we need to look at some division. And we're going to be looking at the remainder theorem. So, polynomial division. F of x is equal to d of x times q of x plus r of x. Right? These d, q, and r are representative of what you would normally have for division, which is your divisor, your quotient, and your remainder. Right? So, what we want to find out is what happens when we divide f of x by x minus k in this case. So let's read this here. If a polynomial f of x is divided, the x minus k is divided by the x minus k. I think there's a word missing there, but anyway, you divide f of x by x minus k, then the remainder is r equal to f of x. Well, this is a lovely statement, but why does it actually happen? Well, consider this. F of x is equal to d of x times q of x plus r of x. Yeah? I just rewrote our formula here. So now let's look at f of x is equal to x minus k plus q of x plus r of x. Right? We want to find out, we want to know if this is true, right? If f of x is divided by this guy. So another way to rewrite this polynomial division is that should be f of x divided by d of x is equal to q of x plus r of x over dx, right? It's the same thing. We just divide everything by our divisor, and this is what we get. So we want to know when f of x is divided by x minus k, we have that r, our remainder r, is equal to f of k. So let's keep going with this. So let's plug in k. Then we get f of k is equal to k minus k. That should not be a plus. This is a times, sorry. Times q of x plus, or q of k, I should say. That's a bad looking k, but it's a k. Plus r of k. And so f of k is equal to, this is just 0. 0 times anything is going to be 0. This is equal to r of k, which is just r, our remainder. Okay? So hey, it works. When we plug in, so like if this is, say, a root of polynomial, well, actually, we'll get to that later. Let's do an example to show exactly what's going on and put some actual numbers behind this. So if you look at this example, which is very small and blurry, but x squared minus 5x plus 6 all over x minus 4. There's no real good way of positioning this camera to work properly. Anyway, we look at this example, and we want to divide x minus 4 by this function. What do we get? Well, this is our f of x over d of x kind of deal, right? So what we can do is plug in f of 4, and that gives us what? 4 squared minus 5 times 4. That's a bad 4, but it's a 4, plus 6, which equals 16 minus 20 plus 6, and that's equal to 2. Yeah. All right. So hey, by this theorem, this is what we get. Our remainder should be 2. Another way to look at this is by doing synthetic division on this. Synthetic division is actually quite helpful. So if we look at 4, pretty sure you guys have either read about it in the book or gone over it at some point previously, but synthetic division is quite useful for factoring sometimes. Coefficients are 1, -5, 6. Okay. And we want to divide x minus 4, so 4 goes out here. 1 comes down. 4 times 1 is 4. Add this together, we get -1. 4 times -1 is -4. Add that together and we get 2. And this guy is our remainder. Pretty sure I spelled that wrong, but it doesn't matter. Anyway, they match up, which is nice. Right? This is how we would usually find our remainder. And now we have this other way because of remainder theorem. Okay, let's go on to another example. Suppose f of x is equal to this terrible looking function, 2x to the 5th plus 4x, 2x to the 5th plus x to the 4th minus 3x cubed plus 4x squared minus 3x plus 8. Evaluate f of 5/2. So in essence, what we're trying to do is we're trying to say f of x divided by x minus 5/2, right? Now, you can, of course, evaluate this and just plug in 5/2 into all of this and evaluate, but that's a new level of torture, which is terrible. So instead, we're going to use some synthetic division because we know that f of 5/2 just means that we're going to be taking f of x and dividing by x minus 5/2. Okay? So if we set up our synthetic division stuff here, what are the coefficients along this polynomial? Well, we have 2, 1, -3, 4, -3, and 8, right? Yeah. Okay, so now this first term comes down. We get 2. 5/2 times 2 is 5. Add that together, we get 6. 5/2 times 6 is 30/2, which is 15. Add that together and we get 12. 12 times 5/2 is 30. Yeah, 30. Add that together and we get 34. These numbers are not looking nice, but it will work out in the end. This turns into 85. Yeah. Add that together and we get 82. 82 times 5/2 is big number, 205. And so 205 plus 8 is 213. And voila, this is our remainder. And we have that f of 5/2 is equal to 213. Okay, this is much nicer than just plugging in f of 5/2 into that monstrosity. So, right, polynomial remainder theorem, polynomial division example. So let's keep going with more examples, but at this time, rational zeros. And we're going to be using synthetic division a bit more too. But first, let's go over the rational zeros. Suppose this is our function g of x, 18x cubed minus 131x squared plus 226x minus 105. Terrible numbers, but hey, it boils down to 2x minus 3 times 9x minus 7 times x minus 5. Right? So the zeros of g of x are, well, you set each of these terms equal to 0, and we get x is equal to 3/2. This one will be 7/9, and this one will just be 5. 5. Okay. All right, pretty straightforward so far. How are the zeros related to the leading coefficient in the constant term? Well, leading coefficient is 18. Our constant term is 105. Well, let's look at the numerators. The numerators are right, 3, 7, and 5. And the denominators are 2, 9, and 1, right? Because you can think of 5 as 5 over 1, right? It's the same thing. So what you'll see is that the numerators are all divisible. 105 is divisible by 3, by 7, and by 5. Same with 18. 18 has divisors 2, 9, and 1. Okay, so this brings us to something much more important. The rational zero test. Now, if you have a function f of x that's a polynomial with integer coefficients, right? Suppose that we have that. Any rational zero of f has the form p over q, where p is a divisor of its constant term and q is the divisor of its leading term. So I'm going to go back real quick to this page right here. These were the zeros of this function, this polynomial. The numerators, p and q, right? These zeros have the form of p over q, where the numerators are divisors of this guy, right? Okay. Now, okay, so any rational zero of f of x has the form p over q, where p is a divisor of the constant term and q is a divisor of its leading term. Why? Well, it's because, well, if we look at, let's look at part of the other one that has x equals 3/2 and 7/9, right? This will make some of the numbers a little bit more bearable, but we have 2x minus 3 times 9x minus 7, right? This is how we got the zeros. This is equal to 18x minus 14x minus 27x plus 21, right? So as you can see, when you put this back into linear form here and multiply things out, you get your numbers exactly back, right? The rational zero test is very nice because once you find 1 0, you can use synthetic division to find the other ones, to find the other zeros much more easily. And to do that, well, and we're going to do that right now. Go on with another example. Okay, so our leading coefficient, what is this? Our leading coefficient is 1, and our constant term is a terrible number 375, which happens to be 3 times 5 squared. Okay, so the possible zeros are plus or minus 1, 3, 5, 15, 25, 75, 125, 375, right? So it would be something like 3 over 1. That gives us 3. And technically there's another 1 in here, right? So it's 1 times 3 times 5 squared, right? Anyway, it can be 1, 3, and 1, 5 divided by 1. 1, 3, and 2 5s gives us the whole thing. 5 squared, that just gives us 25, right? So those are all the possible zeros that we can have. Now, these aren't the nicest of numbers to work with, but hey, if we look at h of 25, that's equal to 0. Right? If you plug in 25 in for this, we get that the function is 0. So that means x minus 25 divides this function nicely. Okay, so let's show that through synthetic division. So we have 25. Our coefficients are 1, negative 22, negative 80, 110, and 375. I'm just breaking that off so it doesn't get too confusing. Okay, so now, 1 comes down. 25 times 1 is 25. Add that together and we get 3. 25 times 3 is 75. Add that together, we get negative 5. 5 times 25, 125, and it's negative. Add that together and we get negative 15. Yeah, negative 15 times 25 is negative 375. Look at that, we get 0, which is good because now this guy does actually divide h of x. And so now we have h of x is equal to x minus 25 times, right, what we have left, which will be x cubed, coefficient of 1, plus 3x squared minus 5x minus 15. Okay. All right. So now let's look for another 0. This is a polynomial that is, well, easier to work with. So now if we look at h of negative 3, that's also going to be 0, right, in here for this function, or this part of the polynomial. Well, that would mean that x plus 3 is a divisor of this polynomial. Well, let's check that. Negative 3. Coefficients are 1, 3, negative 5, negative 15. 1 comes down. Negative 3 times 1 is negative 3. That'll be 0. 3 times 0 is 0. Add that together is negative 5. This becomes positive 15, and then that's 0. So this guy checks out, and we get that h of x is equal to x minus 25 times x plus 3 times what we have left over here, which will be x squared minus 5. Right? Yeah. And so this can be boiled down a little bit more. So I'm going to go up here real quick. X squared minus 5 equals 0. X squared is equal to 5. And so we get that x is equal to plus or minus the square root of 5. Yeah. So this guy is equal to x minus 25 times x minus 3 times x minus the square root of 5, x plus the square root of 5. You might not be able to see that at the end, but yeah. So the zeros for this function, I ran out of room, but the zeros are 25, that should be a plus 3, negative 3, positive square root 5, negative square root 5. Okay. So in the beginning, find the leading coefficient and the constant term, factor them out, find all of our possible zeros, try and find one that, okay, find our possible zeros, and then go through these numbers, plug them into your function, and see which one actually gives you 0. Or you could technically jump straight to synthetic division. But check that it gives you 0. Okay, use synthetic division to cut down your polynomial into something easier. And then keep doing that until you find all the roots. Okay, so this thing has four real roots. All right, let's look at another example. Find all the real and complex zeros of this function. Well, what are the possible rational zeros? Well, this is our constant term, 1 for our leading coefficient. So it's going to be plus or minus 1, 2, 3, and 6. Okay. Now, take a stab in the dark and figure out what's going on. We're going to say 2. And if we plug in 2, we get 8 minus 4 times 4, 16. So that's negative 8 plus 14 minus 6 turns out to be 0. So x minus 2 is a factor of this polynomial. So let's do some synthetic division. 1, negative 4, 7, negative 6. 1 comes down. 2 times 1 is 2. Negative 2 becomes negative 4. Add that, we get 3. Multiply as 6 is 0. So f of x is equal to x minus 2 times x squared minus 2x plus 3. Okay? This guy is a quadratic that cannot be reduced. So we're going to have to solve this via a quadratic formula. So our a value is 1, our b value is negative 2, c value is equal to 3. So from quadratic formula, we get x is equal to 2 plus or minus square root of 4 minus 4 times 1 times 3 is 12 all over 2a, so that's just 2. So this is equal to 2 plus or minus square root of negative 8 over 2. This is 2 plus or minus 2 square roots of negative 2 all over 2. Simplifies to 1 plus or minus square root of negative 2, which is 1 plus or minus 2i. So the real zeros I cut that off too much. This is still a 2. So the real zeros is just x equals 2, and then complex. Technically, you could just put them all together. So yeah, I'm just going to say zeros are 2, 1 plus 2i, 1 minus 2i. Okay, so those are all your real and complex zeros for the function f of x. Okay, so when you start looking at your possible zeros, 1 and negative 1 are your pretty much go-to ones to just plug into your function and see if they work or not. Typically, you work from the bottom up. So like you would plug in plus or minus 1 first instead of 2 or 3 or 6, but that just comes with practice and looking at the polynomial and getting, well, basically a hunch of seeing which one will actually work. But anyway, once you find that first zero, it makes things a lot easier. All right, one more example. F of x, factor f of x in the complex numbers. Okay, so let's still look at the possible zeros. Possible rational zeros. Well, coefficient of 1 here, coefficient of 12. So we have plus or minus 1, 2, 3, 4, 6, and 12. Right? Okay. So this is where I'm going to look at plugging in plus or minus 1 into this. If we plug in 1, we're going to get 1 plus 2 plus 1 plus 8. That's 12. Minus 12 gives us 0. So hey, f of 1 is equal to 0. Cool. So that means x minus 1 is a factor of this polynomial. So if we use some synthetic division, this is 1, 2, 1, 8, negative 12. 1 times 1 is 1. That's 3, 3, 4, 4, 12, 12, 0. Okay. So from this, we have that f of x is equal to x minus 1 times x, we started with a 4, so this goes down 1, x cubed plus 3x squared plus 4x plus 12. Okay, so now let's look at this guy and break it down even more. The possible zeros of this guy, well, they haven't really improved because this is still a 12 and a 1. So these are still the possible zeros. And one of them that works is f of -3 equals 0. So x plus 3 divides this polynomial. In fact, if we did x minus 3 equals, if we did x minus 3 first on this guy, we would have gotten fewer factors, actually, for possible zeros next time. But you can look at the other notes for that. But this is the way that came to me first. So x minus 3, so let's look at -3 and do some synthetic division. 1, 3, 4, 12. 1 times -3 is 3. That's 0. This can be 0 is 4. And this is -12, 0. So now f of x is equal to x minus 1 times x plus 3 times x squared plus 4. Okay? So this is an irreducible quadratic over the reals. So we factor it in complex numbers. And when we do that, we get f of x is equal to x minus 1 times x plus 3 times x, what is this? Plus 2i, x minus 2i. Yeah. So you said x squared plus 4 equal to 0, solve for x, and this is what you should get. Okay, cool. Factoring things is important. Synthetic division is important and takes a little bit of time sometimes. All right. Now for something completely different. I skipped over the meme, sorry, but I at least said it. Now, rational expressions. A rational expression is a quotient of two polynomials. So we could have x squared plus 9 over x minus 1. That's one of them. 4 over x minus 3. 6x cubed plus 9x minus 5 halves all over 1, right? That's a rational expression. So yeah, any two polynomials, quotient of any two polynomials is a rational expression. So what can we do with them? Well, there's a few things that we can do. Most of it is the same stuff that we can do with numeric fractions. We can simplify them, multiply and divide, add and subtract. Okay? So, and it works pretty much in the exact same way. However, we have some differences when it comes to simplifying things. So true or false? True or false? 2x squared over 3x is equivalent to 2x over 3. Well, if x is 5, sure, that works. If x is -3, sure, that works. If x is 0, though, we have a problem. So this is false. What is a true statement is 2x squared over 3x is equivalent to equals 2x over 3 when x is not equal to 0. This is true. So, equivalence. Two expressions are equivalent if they produce the same value at every input and have the same domain. For the last example, or it's right here anyway, they do not have the same domain. So they have to have the condition that x is not equal to 0. This makes everything okay. If we don't have that, then bad things can happen. So let's look at some examples of simplifying and how to do them. A rational expression is simplified if its numerator and denominator have no common factors. Simplify, we utilize the cancellation property. AC over BC is equal to A over B, where C is not equal to 0. Right? And so we have to remember where expressions are defined in order to do this. So if we look at this thing on the left, well, this is equal to 2 times k plus 3 over 4, which is k plus 3 over 2. Right? We didn't do anything with k's, nothing happened. There's no restriction whatsoever that needs to be placed. This guy, however, the top factors into y plus 8 times y minus 2. Denominator factors into y minus 2 times y plus 2. Now we can go ahead and we'll get another color. We can go ahead and cancel these, provided and get y plus 8 over y plus 2, where y cannot equal 2. Right? This is our entire c value, if you will, from here. This whole expression, y minus 2, cannot be 0. So y cannot be 2. Okay? Pretty straightforward, but can be tricky sometimes if you haven't factored out your polynomial on either the numerator or denominator completely. So let's look at some of these examples. This one over here, x squared minus 8x plus 15. That factors into x minus 5 and x minus 3, sorry. Denominator, x squared minus 7x plus 12, that factors into x minus 4 times x minus 3. This is a minus on the top, not a plus. Anyway, so this equals x minus 5 over x minus 4, where x cannot equal 3. Right, so these two things can cancel so long as x does not equal 3. All right, let's look at this function, or these two functions. This rational expression, numerator first, x cubed plus x squared plus 5x minus 14. This does actually simplify. Let's look at the denominator first. The denominator, that factors into something more easily. So this is x minus 9 times x minus 2. So if we wanted to cancel stuff out, x minus 9 or x minus 2 would have to be divide the numerator. So we're going to divide f of x by x minus 2, right? And if this one doesn't work, well, then we know the other one works. So 2 divides, let's see, this is a 1, -1, 5, -14. This is 2, this is a 1, 2, 7, 14, 0. So we get x minus 2 times x squared, this is a 1, that's a 1, minus x plus 7. Minus, that should be plus. Yeah, so now x minus 2 and x minus 2 cancel, and we get that this turns into x squared plus x plus 7 all over x minus 9, where x cannot equal 2. Okay. So that's simplifying some rational expressions. Next lecture is going to talk more about rational expressions, but right now this is the end of this lecture.